Next, we have Stephen Schaefer from Michigan, and he's going to talk about how to reason about parsers and grammar theory in Dependent Lambek Calculus.
Yes, hello. So I'm Stephen, and this is work from me and my collaborators Nathan, Pedro, and my advisor Max, who's here if you guys want to chat afterwards. So parsing is one of the oldest and most studied problems in computer science. And in its simplest form, I mean, a parser is going to take some unstructured text and maybe turn it into a structured representation like a syntax tree. And I'm sure we're all familiar with parsers. Despite what people might frequently say, parsing is not a solved problem, and the cost of insecure parsers can be quite severe. So for instance, many critical real-world vulnerabilities arise as parsing vulnerabilities, including the Equifax hack from 2017, which leaked the financial data of 150 million Americans, probably like a third of the Americans in this room. And for the people here at PLDI, verified parsing is also important because unverified parsers can jeopardize the guarantees of otherwise verified software. So for instance, early versions of the CompCert verified compiler didn't have a verified front end, and the C-Smith bug finding project found 0 middle or back end bugs, but it found 6 parsing bugs, meaning a user of CompCert as an end-to-end system has a slightly weakened correctness theorem that they can leverage from this as a verified compiler. So to verify a parser, we got to give a specification for what a verified parser is. And for me, a parser for a formal grammar A is a partial function that takes in strings, or sends strings to parse trees of that formal grammar A and might fail, so it is a partial function. And when we verify these parsers, we want to verify 2 key properties. One, we want to verify that the parser is sound, meaning for some input string W, when the parser claims to have returned a parse tree f of W, it's a valid parse tree for the proper input, or for the proper formal grammar A, but it better ought to be a valid parse tree for the same input string W, so the parser doesn't change the resources being parsed. Further, we want to verify that a parser is complete, meaning that a parser returns a parse tree whenever one does indeed exist and doesn't prematurely or incorrectly fail. And so with this specification of what a correct parser is, we can take a look at some of the existing verified parsing works. And existing verified parsing implementations often laser in on a single formalism or a single algorithm, such as LVAL parsing, LVAR, or one of these many others. And these are great works, but they miss a key opportunity to reuse some shared kernel of grammatical foundation between projects, because each of these formalisms necessitates its own verified implementation, and they're often duplicating work by what they mean by parser, what they mean by formal grammar. And so verification of parsers could be made easier if all of these systems could be laid on top of a single foundation. And so in this work, we present Dependent Lambek Calculus as a unifying formalism to describe intrinsically verified parsing. So Dependent Lambek Calculus, or LambekD, is a functional programming language for writing verified parsers, and it's built atop an ordered and linear type system such that parsers written in LambekD are sound by construction. And through a little bit of effort, we can further guarantee that parsers in LambekD are complete. And in total, this is an extensible system for describing several grammar formalisms, their parsers, and even their parser generators. And like I said, it's a linear ordered type system. The way that LambekD is going to encode these existing grammar formalisms is by describing them each as linear types in LambekD. And so I said the word ordered and linear as shorthand for this talk. I'm just going to call these linear types, but I guess precisely I mean ordered and linear here. And we've implemented this in cubicle Agda as an embedded domain-specific language, and in that embedded DSL, we've instantiated verified parsers for some selected demonstrative context-free grammars, as well as written a verified parser generator for regular expressions. So throughout the rest of this talk, I'm going to show you the structure of LambekD and the types and terms, and I'm going to walk you through an extended example of constructing a verified parser for a particular context-free grammar. So to begin, let's look at the basis for LambekD, for Dependent Lambek Calculus, ordinary Lambek Calculus. This is a logical system going back to the 60s for describing parsing deductively as the act of constructing a proof tree in Lambek Calculus. And so if we want to parse a string, say AB, we can decompose the resources being parsed and construct smaller proof trees corresponding to the decomposed string. And what I want to say is that in existing implementations of Lambek Calculus, users often don't write the program to build this parse tree or even build this parse tree manually. Rather, they provide a type level specification for what a parser like input-output pairs of a parser will be. For instance, a user often will specify the string and the target formal grammar, and then this parse tree is not written by the user, but it's synthesized through a search procedure or through a logic programming engine. And what we've done in LambekD, in Dependent Lambek Calculus, is extend the expressivity of the Lambek Calculus by adding dependent types and providing a functional term language for which users can write programs to make these parse trees themselves. So let's take a look at some of the types in Dependent Lambek Calculus. First, I'll show you a family of types that will correspond to the regular expressions. We can have types corresponding to characters drawn from some fixed alphabet, a type corresponding to the empty string, and then we can combine these inductively via concatenation, disjunction, conjunction, and cleanly star. And so these types represent these formal grammars. But if we take a look at what we mean by cleanly star here and think for a moment, cleanly star is just an inductive type of lists, but linear lists combined through iterated concatenation. And if we generalize from just this particular inductive type to arbitrary inductive types over these family of base types, we can capture not just the regular grammars of the regular expressions, but context-free grammars and beyond. And in LambekD, which I'll talk about a bit later, we can encode even grammars of unrestricted complexity. So let's take a look at how we can then use these types to encode common grammatical concepts. So I've been mentioning this as a linear and ordered system, and I guess I want to show you why. Excuse me. So first, first, we're going to use terms in LambekD to describe parse trees of strings, and in this case, the string cat. So a parse tree of the word cat will correspond to a term built in a context corresponding to the word cat. Here we just decompose the constituent characters, give a parse tree of the characters C, A, and T, and then we can combine them with the following term to spell cat. And if we want to maintain the interpretation that parse trees of strings correspond to terms built in a context corresponding to that string, we have to restrict the types of terms we can write in LambekD to preserve that interpretation. For instance, LambekD is ordered and has no exchange rule because while reading a string, I don't get to permute the characters. I have to parse them in the order they're handed to me, so CAT doesn't spell act. Similarly, we have no weakening rule because you have to read all the characters in a string. You're not allowed to drop any. And we have no contraction rule because you don't get to read the character T twice, for instance. And it's precisely these restrictions that ensure derivations in LambekD are sound by construction because all the fundamental building blocks in this language necessarily preserve the grammatical content of the resources of the strings being parsed. So this is one way we can use the terms in LambekD to describe parse trees of particular strings. We can also use terms in LambekD to describe reductions between grammars. So let's start with a pretty simple observation. All strings parsed by the grammar A concatenated with A star are also parsed by A star. And this can be witnessed through a very simple flattening function, which in LambekD is 2 lines of code. It really is maybe an extra line because of spacing. And so this flattening function is taking in a parse tree of type A concatenated with A star, which is just a list of tuples, and is flattening it to a single list. But because this type checks in this linear ordered system, this is carrying the data of being a reduction from parses of the input grammar to parses of the output grammar, while still being a very simple functional program that's quite easy to write. Okay, so with these types and terms in mind, I'm going to walk you through the construction of a verified parser for the Deke grammar of balanced parentheses. So the Deke grammar of balanced parentheses is a context-free grammar that's quite often written in the syntax of generative grammars as having 2 productions, one corresponding to the empty string and one that builds up parses of the Deke grammar from smaller parses. And similar to the cleanly star case, if you squint your eyes, this is just an inductive type with 2 constructors, one for each production. The nil constructor says that the empty string is balanced, and the val constructor corresponds to the second production. And just as we parse the word cat, we can parse strings into this grammar by building terms out of a context corresponding to that string. In this case, an open paren followed by a closed paren repeated twice can be parsed into the Deke grammar by building the following term by invoking these constructors in the following order to build this parse string. So with this formal grammar as an inductive linear type in LambekD, we're now going to build a parser for this formal grammar. And let me reiterate what I mean by parser. A parser is going to be a partial function from strings to parses of the Deke grammar, and we'll represent that in LambekD as a function that takes in an arbitrary string and maps into the maybe monad acting on the Deke grammar, so either returning parse of the deep grammar, or top, where top corresponds to failure of a parser. And we can write functions with this type signature in LambekD, and their soundness is guaranteed for free by the ordered linear type system, but the completeness of a parser with this type signature is not guaranteed. For instance, we can always choose to fail, and that would be a very incomplete parser. So if we refine our notion of what we mean by like parser, we can also guarantee completeness in LambekD quite simply. So I'll say instead of a parser being a function from string to deque or top, a complete parser for the deque grammar is a choice of a complement grammar, suggestively named deque complement, and a function from string to deque or deque complement, where we've reduced the completeness proof to the statement that deque and deque complement are disjoint, meaning that their intersection is empty. And so to build one of these, to build a complete parser for the deque grammar, I'm going to use an automaton and encode an automata formalism within LambekD. So taking a look at the following machine, this will serve as the parser for our grammar, and this machine has a state for each natural number, and will increment the state every time we see an open paren, decrement every time we see a closed paren. We want to capture the structure of this machine within LambekD by encoding it as a linear type, and the linear type that we're going to use is this inductive linear type of traces indexed by 2 pieces of data, where we'll tag it with a Boolean, marking if the trace is accepting or rejecting, and a natural number that marks what state that trace begins at. And each of the constructors of this inductive linear type correspond to small modular ways we can build traces. For instance, if we want to terminate a trace in the initial state 0, because that state's accepting, we can use the first constructor. If we want to terminate a trace in the non-zero states, which are rejecting, we use the second constructor. And then the push, pop, and unexpected constructors correspond to different families of transitions. For instance, push corresponds to the open parens, pop corresponds to the closed parens, and the unexpected constructor corresponds to a failing case where we try to read a closed paren while in the initial state 0. So we have captured the structure of this machine as an inductive linear type in LambekD, and we can now build a parser for it. So here's the code that implements the parser for those types of traces. And again, it's a small, ordinary functional program, quite simple and short to write. But because this type checks in LambekD, this carries the data of being a sound and complete parser, and it's complete because the type of accepting traces is disjoint from the type of rejecting traces. And then we can use this code to build a parser for the deque grammar as follows. So the code from the previous slide defines an equivalence between a type of strings and a disjunction between accepting and rejecting traces starting at the initial state. We can separately prove that the deque grammar is equivalent to the type of accepting traces. So this is automaton is indeed a parser for the grammar we wanted it to be. And then we combine these equivalences to build a function from the type of strings to a disjunction between the deque grammar and the rejecting traces out of the initial state. And this is precisely the specification for a complete parser we started out with. So to recap what we've done in this example, we've described a reusable framework for verifying a parser for a formal grammar by describing that formal grammar as a linear type in LambekD, by describing a corresponding automata formalism also as a linear type in LambekD, proving those two equivalent in the equational theory of the system, and then using that equivalence to instantiate a parser for that formal grammar. So we've done this for the deque grammar that you've seen here, but we've also done this for an LL1 grammar of arithmetic expressions and a look-ahead automaton. And we've also done this for a verified parser generator for regular expressions, abstracting over the regular expression, generating the corresponding finite automaton, and reasoning about that equivalence again in LambekD. And so just to reiterate what's happened here, we've taken 2 grammar formalisms that are a priori on different formal footing, automata and the corresponding context-free grammar, and we were able to reason about that equivalence in the equational theory of our system. And so there's a bunch of great stuff that I've elided from this talk that you can find in the paper. We're able to also encode other common grammatical notions within the equational theory of LambekD. For instance, you can prove the ambiguity of grammars within the equational system, and that there's a distinction between this notion of equivalence I keep mentioning, where you can distinguish between grammars being equivalent when they have the same language semantics, when they recognize the same sets of strings, or if they have the isomorphic types of parse trees, and there's more information about this in the paper. I've elided much of our usage of the dependent part of Dependent Lambek Calculus here. So we use linear, nonlinear dependent types as a sort of indexed conjunction and an indexed disjunction that I implicitly used when I said we have a type of traces indexed by a Boolean and a natural number. And these are key to describing grammars of unrestricted complexity. And lastly, I've elided much of the denotational semantics of LambekD, which interprets grammars in the category of functions from strings to sets. And this is the basis for our Agda implementation, so you can check the paper or the artifact if you want to know more about that. Moving forward, we're looking to encode broader classes of grammar formalisms and verified parsers as programs in LambekD, such as LL or LR parser generators or forms of context sensitivity. Looking to encode verified semantic actions and plugging them to verified language backends. Everything I've mentioned thus far has been concrete syntax, but we often want to use abstract syntax. And we believe in a modified variant of our semantics. Instead of having grammars over strings, but potentially type systems over tree structured data, you could use a similar method to implement verified type checkers rather than just verified parsers. So just to reiterate, LambekD is a functional programming language for building verified parsers, and we use the type system to carry a lot of proofs of correctness about our parsers. Thank you for listening.
Hi, my name is Mark Muller. I'm at Cornell. Great talk, thank you. I was wondering if the completeness guarantee requires the grammar to be deterministic context free.
I think no, and that you only need this to straightness constraint. Yeah, there's no necessity of being deterministic or unambiguous or anything like that to guarantee completeness.
Okay, I was just interested by the use of the complement and that what deterministic context free languages are closer in complement, but arbitrary context free grammars aren't. So that's what I was worried about.
Thank you.
Thanks for a very great talk. I'm Yuda Urabe from Science Tokyo. And I would like to ask why you choose denotational semantics to why did you consider denotational semantics? Is it easier to implement denotational semantics in Agda than operational semantics? Or
so you're asking why we use denotational semantics as like our strategy here?
Yeah.
I'd say it makes precise what we mean by the formal grammar semantics, and I guess this is my first project, so it's a notion of like what's easier if we were to do this operational or not, I don't have a necessarily a good read on, but it at least makes precise what we meant by the formal grammar semantics, and sort of, for me, I value that precision, but maybe we could talk afterwards about some of the trade-offs. Yeah.
Okay, thank you.
Yeah.
Hi, I'm Sarah. Thank you so much for the great talk. And I'm from University of Michigan as well. So you mentioned like you were able to like prove ambiguity, but is it like enough to have linear and ordered typing constraints to do that, or did you also added anything to like deal with the ambiguity?
I have to think about that. Can we talk afterwards about that?
Definitely.
Sorry. Yeah.
Questions? So I have a question. Using Lambek calculus, can you prove meta theorems like the closure, the intersection of two regular languages is regular, or homomorphic image of a context-free language is context-free, that sort of thing?
This is a great question. I would expect yes, but I don't know like how complex that construction might get. But in principle, you could like capture the class of regular grammars and then like map between them as terms in LambekD and hopefully prove this closure procedure. But that might take a lot of manual work that I think is lost on me in this moment at least.
Thank you. Okay, let's thank the speaker again.